Okay, so for the chapter heat and work, in fact, there's only one question that is completely from this chapter. All of the subsequent questions use something from the first law of thermodynamics. So in this tutorial, we're going to be solving only this question. And after this tutorial, there's going to be a relatively short lecture on first law of thermodynamics. And then after that, we're going to be looking at all of the questions of heat and work chapter. uh, I'm doing this because I would like to tell you something about the first law of thermodynamics or give you a basic introduction to it before we fully delve into heat and work questions, right? So with that being said, let's quickly solve this one question. A 400-liter tank A contains argon gas at 200 kilopascal and 30 degrees Celsius. Okay, 400 liter, 0.4 meter cube. Always write volume in meter cube. We are using the physics units here, we are not using the chemistry units here. Contains argon gas at 200 kilopascals and 30 degrees Celsius, and cylinder B having a frictionless piston of such a mass that a pressure of 150 kilopascal will float it is initially empty. Okay. The valve is opened and argon flows into B and eventually reaches a uniform state of 150 kilopascals and 30 degrees Celsius throughout. Okay, so finally we have some volume of gas here and some volume of gas here at 150 kilopascals and 150 kilopascal, 30 degrees Celsius and 30 degrees Celsius. This is the uniform state. State 1, state 2. Right. What is the work done by the argon? Okay. So, as you know, work done is integral of PdV. Now, what is this pressure? This pressure is the opposing pressure against which the work is done. Now, if we read the question carefully, we can see that a pressure of 150 kilopascal will float it, and the uniform state of 150 kilopascal is reached, which means throughout the pressure must have been 150 kilopascals. So the argon gas throughout the process is doing work against a constant pressure of 150 kilopascals that is exerted by the piston. An important thing to keep in mind is that it is not 150 kilopascals plus atmospheric pressure, right? In the question, it will give you the total pressure that is required for the piston to move. So don't do it like 150 kilopascal for the piston plus an additional PATM of, I think it was 101 kilopascal. Don't do that. The pressure given in the question is the pressure that you have to find the work against, right? Now, as 30 degrees Celsius is constant throughout the process, it means that it is an isothermal process. So, P1 V1 equals to P2 V2 from PV equals to nRT mRT. We can use this because it is argon, and we have to assume it to be ideal gas. In fact, you can do it using tables, but why would you want to? Using argon gas as an ideal gas, also since it's a noble gas, it will most likely be an ideal gas. So that's why we are able to use this. So 200 into 0.4, remember volume in meter cube, equals to 150 into 0.4 plus VB. Why is this? Because initially A had argon gas of 0.4 meter cube, and finally also that argon gas will expand to fill up A, which still has 0.4 meter cube of available space, plus the gas that goes into B. So 0.4 plus VB. Therefore, VB equals 0.133 meter cube. Therefore, V2 equals to 0.4 plus 0.133, which is 0.533, right? So, W is PdV as pressure of 150 kilopascals is constant throughout, because remember the gas is working against the constant pressure of the piston, right? So work is P delta V equals to P V2 minus V1 equals to 150 into 10 to the power 3, because I'm converting into pascals, into V2 0.533. This is VA plus VB minus 0.4, which is just VA, and it will come out to be 19995 joules or 19.995 kilojoules. That is the only question that I have that is of purely heat and work. So after this we're going to look at the first law of thermodynamics chapter. Our theory part of the chapter is over and our question part is also mostly over. After we look at first law of thermodynamics, we're going to be able to solve a lot more questions that are related to both this chapter and heat and work.